there's 6 viewers, so you're ready to go.
Sure. Cool. So welcome to this afternoon session on the introduction to data analysis with Hadoop. I know it's a Friday, so I appreciate you guys can show up and make it to these training sessions. It's supposed to be 3 hours long. I'm going to break them in mostly like 3 parts, and we are going to have 1 break in between. So this training session is mainly intended for people who are not really familiar with the Hadoop. So I will starting with some introduction on what Hadoop it is and what's the MapReduce programming model, because it is quite different than the traditional HPC, how things working. And also Hadoop is not just a single application or single software you do things, but also there's a lot of like related projects and other tools that based on the Hadoop. So there's a term called Hadoop ecosystems, and that is where you can get more applications and to meet your analysis or data stock management needs. So I will give some introduction on the Hadoop ecosystem as well during the first hours or so. So the first hour will be mainly consist of the slides presentations, just to give everybody a basic ideas on what's Hadoop and how the MapReduce works and the basics. Then we will take 15 minutes break. So after the break, I will more focus on what kind of the resource support we have at TAG to supporting people doing analysis based on the Hadoop. For that part of the slide on the first half, at least, I will do is more like walk through on with the slide with the screenshots to how you can get on our resources, and once you get on resources, what the things you can do, and work through some exercise you may be able to doing later on. So at the last half hour or so, I would like to just hand the things to you so you can actually hopefully log on to our resources and practice some of the Hadoop stuff you learned today. Okay, so if you have any questions during the presentation, feel free to let me know. I would be happy to answer them. And in addition to the in-person presentations, we are also doing this as a webcasting. So there may be some of the people online that watching this. If you have any problems, we also have a chat windows available right now. You just send a chat under your question, or if you have any problem in hearing us or seeing the presentations, just feel free to let us know. So we will try to addressing those questions there. Okay, so the Hadoop is motivated by things called the big data, right? So I want to give a couple of slides briefly on what's a big data and why the big data promoting these changes of how people can do the analysis. So big data became a popular term nowadays, but it's actually some concept that has been existed for quite a long time for scientific communities. So one of the guy at Microsoft named Jim Gray, I don't know how many of you heard of him before. He's one of the founding persons of behind Microsoft SQL servers, and he has been in sort of data-oriented research for quite a long time. A few years back, and he published a book named The First Paradigm, where he thinks the big data can be treated as a first paradigm, how people may be able to know the world and doing the research. So the first paradigm is referred to how people doing scientific discoveries, and since very early on, very Stone Age, we're doing more like theory-based scientific advancements. Then we move on to the experimental, then we move on to the simulations-based scientific discoveries. Now the big data, what the big data can promote is people hoping to, through the data, mining through the large scale of the data, that be able to getting more insight that can help us to know scientifically or socially better. So the big data is really comprised with the 2 aspects. One is this is increased volume of the data, where the more data you have, then some things that used to be insignificant that now maybe became a significant part. And then the increased volume of data can help to improve accuracy of many of the existing algorithms as well. The other aspect is the increased complexity of the analysis. Another trend in the big data analysis is not only you have sheer volume of increase of data you need to process, but also you want to process the data that may be across two different types and across different domains. So in the recent years, there's quite a few researchers contacting us and trying to do some new researchers on data related, and some of them is they never thought about to do before. So one example is we're collaborating with some people doing the transportation research, and they were used to do just a model-based simulation. They have a traffic model, they need spatial data, and they put into the big simulation and to run the traffic simulation and getting the data there. And now a trend in the traffic research is actually trying to join that sort of method with a social media data to help them to understanding better how people actually move by tracking down where they check in through their Facebook account, through their Twitter account, or through their Foursquares. So that opens a new dimensions for researchers how they can do and handle how they can do research with their own domain fields there. So there's a lot of wonderful things with big data there. And now today's, we are not going to repeat them, but also we're more focused on how we can helping people to do better with the big data analysis. So before we continue, let me ask a question. What's a big challenge in the big data analysis? Well, we have few people in the room, so what do you think?
Size of the data set.
Yes. I use these slides for my class for the undergraduate students. When I asked this slide, no one responds to me. I told them, see, I had too big in the titles there, right? So the problem with the big data analysis and why it's changing how people doing the research is really the size of the data and the different type of the data there is. So I like to show this image, and this is actually a quite old image now, and I used that for the first time. I'm trying to teach a big data related or data intensive related topics. And what you see here is some of the common data and the estimate on how big it is. So on the top, you may see World Wide Web is estimated as 1 petabyte, and Wikipedia is about 10 gigabytes. At the bottom line, you see the total data to be created this year is 270,000 petabytes or something. So is that a big number to you? Fairly big, right? So another question is, guess which year this image is being generated? There are some hints on the image, right? So 2004, yeah, you see that 2004 Walmart data set there. So we obviously generate that data sometime after that. So this image is actually generated at 2008. So based on the data, the estimate is on 2008. I first saw it in the 2009, 2010 time frames. So that's sort of what people's view on how much big data we have right now. And when time goes on, I saw this is really impressive pictures that people know the scale of the problem. But time goes on, I realized I need a more updated version of it, but I couldn't find it. And the one I can find it is closely, but it's more interested is this one that to show you how many things going on, how many digital data people generating per minute. So that's significant. That's essentially right now the estimate for how many digital data can be generated per year is already in the gigabyte levels, and then there are just a hint of how much those digital data is being generated by so many people online and so many people participating in this generating that create that digital content there. So obviously, the biggest challenge with the big data analysis is the size of the data, or the time, or the type, or the volume of the information that you have to be processed. So the data analysis process will require more computational resources for sure. That resources may including, say, you need more storage resources and to store all those data. And not only it's just the raw data. If you're doing the data mining, data analysis, you know eventually you're going to derive more data from your raw data, and you will have different version of that data, and you will run different analysis, and those will generate more result and more and more data. So you need more storage, you need more memories, and also the analysis process would take much longer. That comes with the two parts. One part is the raw speed on how much your computers can access those informations, right? So mostly you're using the computer, using laptops or regular desktop. For large scale of storage, people typically turns to disk-based storage, and then the typical disk hard drive, spinning disk-based hard drive, the read speed can about 150 or 200 megabytes per second, but that it maybe sounds a big numbers by itself, but if you consider you're reading 1 terabyte data, at that rate, that alone will take like 2 hours for your data just being read off the disk to your for your CPU, for your processing core to process. Assuming that's not a problem, you can put in the 1 terabyte data, you're spending time on there, and you put in them in the memories. And then the analysis, a lot of data mining analysis, taking the time that linear or even quadratic or triple the size of your input data. So some analysis may be taking 1 second when you're having 1 gigabyte data before. Now it could take exactly the same process if it is a quadratic to the size of your input. It may now requires like over 10 days of the processing time for 1 terabyte of those data. So that's sort of the real computational challenge the big data analysis associate. One is the huge storage and the memory requirements, and secondly is eventually the analysis is going to take much longer, and we cannot do that on one computers anymore. So the big data has to be done with some sort of high performance, either higher, newer, latest hardwares, as well as newer, latest technology for that. Till then, people may ask, say, the high performance computing has been around for a while. Say our center especially way before the big data became the popular terms here. So what's the difference between the big data processing versus the traditional high performance computing here? So the big data analysis usually means data intensive computation. So they have high demand of those computation resources. On one hand, those things are aligned very well with what a HPC center like us to do. We're providing resources. We have much more powerful hardwares, and we have a lot of storage resources for you to store your data and to processing them, and a lot of processing cores. The question here is what is really how, and what's the best way to putting those high performance computing resources to be used and to be effective with data. Somehow was just logged out.
You're back on. You just have to share your screen.
Am I back?
Yeah.
Okay. Sorry for people online. Somehow I got disconnected a few minutes back. So here is a sort of the simple illustration on how a traditional HPC cluster works. And let's consider a simple use case where we have one user that's trying to use these resources. What he will typically do is he need to log into one of the login node, and then he need to transfer his data through that login node and being stored in the storage devices separately. Once that data being stored there, and he need to submitting a job request, where the job request will assign a set of computing node for this user to use over a period of time. And he need to develop in his code and to utilizing those multiple machines. And in a basic way, each multiple machine will go trying to accessing the data he put in the high-performance storage device and read them individually and to do the processings. So in this kind of the process is so the traditional computations in the HPC centers, the data are typically stored separately, and then we providing high-speed connections between the storage and the computational resources. So the reason for doing that is one is we can increasing the throughput, meaning we can allow more people to share the resources where your data is now tied into any particular computing nodes. But on the other hand, it became too quite troublesome for people when they to use this kind of infrastructures for large-scale data. Typically, they will developing the code that run the multiple nodes concurrently, and then it is users' responsibility to staging the data and to specify how each data can do being read by which computing nodes and to do the processing there. So typically, a master and a slaves model that being used, where the master threads making the control over the multiple workers that to do the processing concurrently. So the MapReduce models is a new model that come trying to addressing the adapting big data analysis with distributed computations. The MapReduce models is different than the traditional HPC models we have been seeing and used to here. So it's a programming model that first proposed and used by Google's. One of the key ideas of these programming models is trying to simplify the process on how the workload can be distributed out and how the analysis can be done distributedly as well. So down to the core of the MapReduce models, there is really an idea of to abstract your computations into two kind of major phases. One is the map phase, where you want to distributing your data, you want to distributing your analysis works, and capture those analyses you run on individual data on your raw data input as a map functions. And then there's a reduce phase where they collecting those results of each individual result, each individual processing result from your map task and generating your final process, final results. So the basic idea of MapReduce is not really something brand new. It is an old idea we call divide and conquer. And you want to divide in your huge data set into smaller chunks, then having the different nodes to process them at the same time. But there are a few good ideas being embedded in the MapReduce models, and that makes that MapReduce model different than the traditional HPC processing models. So first, the big ideas in the MapReduce is in the MapReduce models is trying to move the computation to the data. It doesn't really assuming your data, there is a high bandwidth connection between your data and the storage resources. And by doing so, they are trying to assume the data is local to the processings in order to avoid and reduce the need you need to transfer data over the network. So instead of say, I have these computations to run on this node, then for this node, go fetch some subset of data. The idea in the MapReduce is really, I have this number of processing I need to be done on all my data. For this node, it only need to processing whatever the data this node has. So the processing, we just need to put in the code into the node, and the data is already in that computational node. The other big things in the MapReduce is by doing not really fetching the data explicitly, they can do a better job in terms of the organizing that data locally as a large chunk of the sequential records, so the data can be read in a sequential fashions rather than a random access. The sequential reading is a sequential read of the data is a idea that has been implemented with the database where people can build index and to searching over large volume of data quickly. In the MapReduce models, your data, when you store them in the Hadoop clusters, is being packed into a much larger chunks, or they call it blocks. And then that blocks is being processed as a whole by the map task. There are some other ideas in the MapReduce. Is the whole basic ideas in the concept in the MapReduce is trying to scaling the computations by scaling them out rather than scaling up. So then in the computational term, the scaling out is we want to get in more nodes to be able to make our code running better, running faster, and running in a scalable, rather than we getting, say, a very expensive hardware to improve the execution time for programs. The benefits of doing scale out versus scale up is it is very easy for your code to be really elastic in terms of the hardware you are available. So the same Hadoop code you're developing could be run with just one node. That runs fine, it's just taking longer time. But the same node could work on if you have 100 nodes in your clusters, and you will just get the benefits of running hundreds of the map, hundreds times more map tasks concurrently, if your data is big enough. The other things makes the MapReduce model very popular is the system or the platform trying to hiding the hardware details from end users. So for the end user to do the programming, it doesn't really need to consider too much on what kind of parallel computational resources I'm going to run it, in what kind of the protocol or what kind of models. In the MapReduce model, there is just one way you can specify your analysis in terms of map and the reducers, and then it can run whether you have a set of DNX clusters or a set of heterogeneous clusters, or there are some implementations, say Hadoop on top of the GPUs. The same code could be run there as well. So that's about the basics, about the concepts in the MapReduce models. Then the main topics of today is about Hadoop. So Hadoop is a open source. The MapReduce is a programming model, or sort of the ideas how we should processing the big data, how the big data should be done in a more efficient and elastic ways. Then the Hadoop is a open source implementation of the MapReduce programming models. It is a native Java application, so it's written in Java. You can use it as a Java library. Now it's became more than a library, but really comprised like a platform on how people may be able to do analysis and process weights. Although it is implemented in Java, it has a lot of interface and feature support that you can actually run analysis written in different programming language easily with the Hadoop clusters. The Hadoop clusters, when we mention it usually at the core, it will include several components. One is the distributed file system. In short, it's a HDFS. It is a open source implementation based on Google's file systems. They use internally, and it's a shared distributed file systems. That's the core to serve how your data being divided, being distributed out across multiple nodes. The other core component in the Hadoop cluster is called Yarn, which stands for yet another resource managers. As the name implies, it is resource managers and trying to match the resources that are currently available within the Hadoop clusters to a user request or to users MapReduce tasks. Then they have a MapReduce library where it's an interface on how people can developing MapReduce type of code and running under the Hadoop easily. And there are a few other projects and libraries available, helping people along with the big data analysis. One of the machine learning libraries called Mahout. It's another Java library, but includes a set of the scalable machine learning and the data mining algorithm that already implemented and works with Hadoop clusters. The other popular features with Hadoop clusters is Hadoop streaming. Hadoop streaming is another Java library that enables people can easily pipe using programs or analysis routines developed with other programming language and to use with Hadoop clusters. So for today's, I will quickly go through what's HDFS and what's Yarn and and we will have some example and the introduction on Mahout and Hadoop streaming as well. Okay. So for you in the several slides back, you saw what a typical HPC infrastructure looks like. Here is a typical Hadoop infrastructure looks like. So in these pictures, and similarly, you will have a login node where people can log in and so serve as a client. And under the clusters, you typically have a difference between a small set of the nodes that are being used as a service node. The most commonly is one node is being used as a name node, while the majority of the nodes that are being used as a worker nodes inside that Hadoop cluster. So in this case, the name node, it's responsible for managing all the data node, and the name node, the name of the name node is actually means that node holds a large namespace and to map where your data is stored in which data node and in which blocks. Typically, you can have multiple nodes for service node. Or in some case, and some other services can run all under the name node. One of the things I want to mention is the resource managers, which is where Yarn running and then running at the resource manager servers, and on each data node, there's a corresponding node manager servers that communicating back with Yarn to let the Yarn resource manager to know what's the computational resources that are currently available and are ready for user to request and to use. So if you just look at these pictures, other than a small subset of nodes, it seems no big difference with a typical Hadoop clusters looks like, a typical HPC cluster looks like. But one big difference here is in the HPC picture I saw in a few slides back, we have a separate storage device. But in this case, your compute node and the data node are the same, and your data is being stored distributedly over all the work node you have. That's where your data analysis will be happen as well. So how exactly does MapReduce work with Hadoop? Is the computations, when you're developing your analysis, you are going to breaking your analysis into sort of two major phases. One is a map phase, and one is a reduce phase. So in the map stage, and you want the map task is processing your raw data stored already in your HDFS and generating a set of intermediate results. And that intermediate set of results is in the format of the list of the key value pairs. Then the reduced instance will collect those key value pairs that generated by your map instances and doing the task that to combine the values that from the same key together and to reduce in order to do the reduction of the results that being generated by the map. So one of the key things during the MapReduce analysis work is this key value pair format of how your data it is. So for the key value pair format, it's just mean two objects. It's similar to the concept you have with a hash table where you have key and you have values. In this case, the key is corresponding to certain identifiers that you can. There could be multiple values to be mapped into the one keys, and then both key and values, they could be any arbitrary data types. So in the Java, both of them could be just a generic object class. Here is a quick workflow on how MapReduce process can work. So your input data is going to be stored as a list of the key value pairs. Then your map process will read the key value pairs that's stored on your data nodes and generating generating a list of intermediate key value pairs as output. Then the output will go through a few other phases, and then the few other phases will combine the key value pairs with the same key together and grouping them into smaller groups and sending each of those groups into a corresponding reducers. Then the input to the reducer will be a key followed rather than by one values. It's typically by a key and a list of values. Then the reducers will act on this key and a list of values and to reduce the result from one key, a list of value to one key and one values. In this process, the workflow may look like there's multiple steps you need to go through, but one of the nice things with the MapReduce programming framework is for developers, and then the two key things or the two absolutely required things to be developed in this case is really just your map process and your reduce process. A lot of other things in between is already have a default implementation, is what the Hadoop clusters can handle for you. So let's look at a sort of examples on how MapReduce works. So I assume everyone has some experience with a certain programming language before. So in the programming language, what you usually learn to that language, they will give you a example code called hello world. Usually it's just a printf hello world. So you see how the program take input and doing output. The equivalent of the hello world in the MapReduce or Hadoop word domains is called word count examples. The word count examples is on the same spirit with the hello world. Instead of taking input and generate output, in this case, the input will be one or a set of text files, and then the output or the processing we want to do is we want to count how many unique words are there, and for each unique words, how many occurrences that word has been appeared. So the typical input is a text files. Could be one or could be multiple of them. Then the output is another set of text files with word and how many times it's being found in that input set of the document corpus. So here's a very simple examples, and just to show how a actual MapReduce programming work processing flow maps to the workflow we show. The abstract workflow we show a few slides back. So in these examples, your input is a simple text file with only 3 lines, and each line has 3 words in there: the deer, the bear, the river, and then the second line is a car, river, and you get ideas. So when you store this text file into the HDFS, the Hadoop clusters can split the inputs and store them into different multiple chunks and being stored at the different nodes. That's just assuming it can be done for this case and for the real Hadoop clusters. So once it's being splitting out, and then you can write a map functions that just counting whatever the input data that particular node has and generating a key value pair. In this case, the key is going to be the unique words you found in the input data, and then the value going to be always just one. You find it and you return the word and then the count of one. Then after the mapping process, there is an automatic process that going on under the Hadoop cluster. It's called the shuffling phase, where the shuffling phase is responsible to gathering the key value pair generating by your map process and grouping them. So all the key value pair with the same key became to one group. So in this case, the first group is gathering your map result from first one and the third one. And then the second one is gathering the result from the second one, the second map instance, and your third instance to the second one. So after the shuffling process, your key value pairs generating by across all the map instance will now become to a few groups that grouped based on the unique keys. And under each group is the same. All the key value pairs share the same key. But doesn't necessarily share in the same value. But for each group, it's then passed to one reduced instance. The reduced instance will work on this key and the list of values and just to processing those values. In this case, we just want to sum all those different values together and generating the final output. So this is sort of the ideas of the word count examples is to given your input data, we're breaking them into different words. Then for each word, we will emit using the word itself as the key and the value one as values. And then that somehow pass to the reduce phase. And then reduce will gathering them and generating the results. Here is a quick look on how the actual code looks like when you're implementing this in Java. This one is an overview. So the total line of the code is about like 60 lines here. There's a kind of three code block here. So the first one, the biggest block is the map class, where you specify what kind of processing or what kind of task to be done during your map stage or during each of your map instance. And then the second code block is a reduce block, where you specify given once your map process is done and then the key and value has been grouping and gathered together and what reduce should do. Then the main function in the map reduce program will just basically setting up this job and tell the Hadoop clusters how this job should be run. So the first one, the map is mapped to the map phase we showed earlier, and the second one is mapped to the reduce phase we showed earlier. Here is a little bit more detail on this mapper process. If you're not very familiar with the Java code and the programming, it's okay. So it's very simple. So the first one is to define them as a class that extending a base sort of mapper class here. Once you're extending this mapper class, and then there's one function you have to implementing for your mapper class called map. And in that map functions, and it will do the major processing. So in this case, the processing itself is really just two things. One is you want to split the lines based on the either input line into multiple words. Then for each of the words, you are going to just write a key value pair as a word, and then one is corresponding to a integer one here as output to your Hadoop clusters. So, the format is messed up here on this slides. But this one is showing the reducer. I hope it's working fine on your slide. You can download online. What we are showing here is a reducer class. Other than the messed up formats, and what it really does is it goes through the input will be one key and the list of the values, and then it will go through that list of values and just sum the value together, and then it will write that key and then the sum of values out as the final output. Here is a typical setup for the main class. Where you want to do is you create a job instance from a factory class. Once you create that, the main thing you want to specify is what's a mapper class you are going to use. So in this case, we implementing this map class, and that's what we want to use. And what's a reducers class we want to use. I will talk about combiners a little bit later. Then you want to set up what's your input format. In this case, it's text input, and what's output formats. And then basically this one is just say I want to run this job and until it either fails or is successfully done. So that's the real implementations. You can have access to that to this simple code during your exercise as well. But you can see that's all it takes to do that programming. Yes.
So do we have to always divide into these functions?
So the question is, do we always have to have both map and reduce functions and being implemented in the Hadoop processings here? What do you think? Any guess? Yes. Yeah, I heard someone nodding. So actually, you do not need both map and reduce program in your Hadoop processing, and there's often the case where you may want just to do the mapping. So your mapping may be able to actually do a lot of works, and sometimes you do not need a reduce at the end. Then you really don't need reduce, but if you are going to implement reduce, there's no way that you cannot implement the map process. So you could have a map reduce or your analysis just running by bunch of the mapping process. So for example, your mapping process could be simply as a search function. I'm just going to searching for all the input data, finding a particular word. Once I find, I'm just going to report this word is in this file or the word is used in this line. Then in that sense, I really don't need a reduce. Right, so so the map process can be worked as alone. so it's a real code you are seeing there. That's a real thing you want to do there. Do you have any other questions about the code you are seeing here? Okay. So go back to the workflow we showed earlier on. What the code is really implementing is just the mapping and the reducing process, right? So when you specify the map and the reduce process, do we need to specify how the file is being distributed out or the splitting process? Do we ever need to worry about that? No, right? So for each of the map process, they just assuming we are going to read a line in, and they do not care which line of your original input file it is. And it's just that as long as I'm having a line, I'm just going to do this job. So there's no need for your code to do that sort of workload distributions there. There's also no, in the code, there's also no any code that implementing how I'm going to send this particular key value pair from my map output to the reduce output. That on my map output code, all I'm doing is just say this particular object called context to write that one out. So that's basically going to sending this key value pair back to the clusters. Then the reduce process will just gather a nicely grouped key and the list out values shared as same key together. So the shuffling process in this process is also handled automatically by the Hadoop clusters here. So for the users really need to implementing, it's just this the two white box. For the blue box, for the first part, the splitting part, is done at the time you're putting your data inside the HDFS and how their data going to be distributed, stored, that's going to be distributedly computed. And then you implement your mapping process, then the in between your mapping and the reducing, you don't need to worry about how that communication to work. You don't need to explicitly collecting that result out to your reduce process, but the system will handle that collection and merging and just parsing a nicely formatted list of one value and the list of one key and the list of values. Then your reduce process will output the result back as another key value pairs. And in the previous code, if you look at the online slide, you will see there's no specific on which file I'm writing into and on how the output I should done I'm doing basically the same thing on, say, just context write this key and this values out. That output will be automatically write down by the Hadoop clusters and into a file theirs. So there's no end output you need to explicitly working on theirs as well. Okay. So on one hand, the MapReduce programming, the model is really trying to simplify how people developing a distributed processing works. Here's some more details about the mappers and some process in between the mapper and the reducers, the sort of more details on how the cluster really implementing them. So the mapper process is always what it always does is to maps a input key value pairs into a set of intermediate key value pairs. So in this sense, the class, so the map class is for individual map class to run. So that's specify your most basic processing is sort of the analysis you are going to run on all of your data and the on all of your data. There are always going to be one mapper task generated for your input split. The input split is another class that defined in the Hadoop clusters that defines how your data is being grouped and being distributed, stored across the multiple nodes here. So in our simple examples, we have one line stored on each of the nodes. That's actually not going to happen with your real Hadoop clusters with your real Hadoop programmings. And also, in this case, the map function will be automatically called per your key value pair. So your input split is consists of a set of the key value pair or your input data, and then the map function you implemented inside your mapper class will be automatically called on each of those key value pairs available through that particular subset of data theirs. So your input key value pairs, I color in blue here, is being your input in your map functions. The context is a system mechanisms and to handling the intermediate input and output. And then your intermediate key value pair you're generating back, I'm coloring orange here, is the one you're writing back into that context object here. Okay. So in the abstract workflows, in addition to mapper and the reducers, there's also two other phases called partition and the combiners and partitioners. Those are two phases that implemented inside the Hadoop clusters. It is a process the mapper what happened after your map process done. So it's what happens after your map process to say, oh, I'm going to write this key value pair to the context. Then the context will run the partitioner and the combiners. The partitioners is to determine which groups you want to put in that intermediate key value pairs in. It will grouping multiple keys into one groups and then later passing that entire groups into a reducer process. The combiners is works on locally right after your mapper process. Usually what it does is trying to if this map process already generating two key value pairs that with exactly same key. So instead of rewriting two key value pairs out, we can actually combine that two key value pairs into one as if we are already running that reducer class. So by default, the combiner class can be exactly same as your reduce class. So if you can, for both of the process, you can have your own implementation to customize what's a grouping you want to do based on the key and how you want to combine them differently than the reducer to do. But by default, the partitioner will using some of the default hash function to do that, and the combiners will automatically call the reduce function you already defined and to work it. So the combiner here is really, you can think of them as you're already running that reducer locally as well. Okay. So this is a two process that automatically happens with every MapReduce project. And it is something if you want to get more performance out or getting more control on the behavior, you can go and override and have your own implementation. But if you do not care, then it's already handled by the Hadoop cluster, by the programming models. Any questions about MIPRE and the combiners? So the other big phases in the MapReduce is a reducer phase. So let's go back. So the code here is much less looking than the previous slides. So the reduce in the reduce phase, the reduce will take in a set of values of the same key. So if you look at the code, the input is one key and a iterable class or a list of the values here. While in the previous case, in your MIPRE process, it will be one key and one value. So it's individual one key value pair being passed into MIPREs, but a value, individual, a key and a list of values being passed by the reducers. So the key, so this key and the list of values is what's the output after the partitioner and the combiner process. So each reducers will process a subset of generated by the partitioners. The partitioner will generating the same number of groups that equals to the number of reducer you requested. Then each reducers will generating one output files out, and it will be written as another key value pair format, and in that particular for that particular reducers. Similarly to the MIPRE process, there are some hidden stage inside the MIPRE process. In the reduce process, there are also some hidden phases in there. So one thing you already saw is I showed in the previous workflow pictures is called the shuffle phase, where the shuffle phase grouping the keys to generating that key and the list of values. The shuffle phase we show simply in that pictures is actually two separate processes in the implementation of the Hadoop MapReduce program models. One process is called the shuffle, where they gather in the partitioning from the different MIPRE. So MIPRE 1 may generating the partitioning based on key A and the key B. Then the key A and key B may also be generating by other MIPRE process. So it is shuffles. It's during the shuffle process, it will go say, I want to this reducer to getting all the key of A. Then I'm going to go to the MIPRE 1 to getting that key to this reduce instance and getting the groups of the MIPRE from MIPRE instance 2 with the same key here. So once the shuffle process gathering those key values from multiple MIPREs in the reduce side, for this particular reducer, you now have a small number of different groups. Each one may be consists of one key and a list of values, and then another and the same key, another list of values because they're coming from different MIPRE instance. Then the sort process is really running sort of like a merge sort process, and to merging the key value pairs you're gathering from the different MIPRE instance, the partitions you get from different MIPRE instance, and putting them together into one larger groups here. So these two phases is already implemented with the MapReduce program models, and it runs automatically after during the most time it's concurrent with your partitioning and combiner process as well. So once the MIPRE is ready to send some keys to the partitioner, once the partitioners done partitions, it will send out to the shuffle phase. In the shuffle and the sort phase, they work at the same time, and while they are gathering new data scene, they're also merging them together as well. For this part, again, and if you're just starting to do the programming and you don't need to really do any implementation for it, it's already being implemented. There are certain algorithms used for gathering the data and for sorting them. But the more you learn about MapReduce and the more you're into the programming side, you may realize this is the bottlenecks or where the efficiencies of different MapReduce programming comes in. just because during the shuffle phase, it actually involves of moving your data from multiple microprocess to a different reducer process. So how you can reduce that data movements often became a key point on how you can improve your analysis efficiencies and improve the overall MapReduce programming works. Okay, so that's sort of like more details behind the simple map and reduce process. And for those, so now it's the two large phase, map and reduce, but for each of them, there's actually like 3 different phases in there. But luckily for the developers, and you are only required to implementing one, and you can using the default implementation for that tool. But if you want more control or more customized actions and more efficiency, eventually you can re-implementing all of those. Okay. So any questions so far about the programming models there? So let me ask you a question. So how many of you have done HPC type of programming? Just one? Okay. Then so most of you really do not have any distributed programming, much of the distributed programming experience before. So when we talk about distributed programming, right? So we want to run things with multiple instances here. Anyone wondering during the process there, we have no any mentioning about how many mappers or how many reducers we want to run, right? So anyone have a question about that? So actually, when you're doing your practice, actually, you will find out how many mappers you use to run it and how many reduce process will immediately become your #1 questions when you're trying to run any of MapReduce programming work. So I get that question a lot when I first teaching those kind of MapReduce programming and or talking with the people to introduce theirs. They often ask, say, how many mappers I should use, how many reducers I should use. So can you guess what my answer is? Yeah, unfortunately, it's always depends. So it's kind of useless answers there. In the Hadoop clusters, the number of mapper and number of reducer is obviously 2 of the most important parameters you are going to be concerning with when you run any MapReduce analysis there. However, you can specify them. I will show you how you can specify them during the exercise, but you need to keep in mind those things you specify is just a suggestion to the Hadoop clusters. It may be used as numbers, it may not use as numbers internally. So when we talk about it depends, right? So the question is what exactly it depends on. For the mapper process, it's more or less depends on your input workload. It's mostly based on how many input split you can have. So in the previous slides here, I show the simple processing flow here. I have such simple input data, and I just show them it's being split into 3 pieces there. But in the reality, that's not going to happen. So you are going to, the Hadoop clusters will not dumb enough to split that 3 small chunks into different nodes and to do the processing. It will be stored in the 1 chunk, right? So if all 3 of them being stored in the 1 chunks, we are not going to have 3 map process running on each of them, and we will only generating 1 map process here and to do the processing there. Even you can specify a mini map process for that data, and the MapReduce cluster will still just generating 1 single map because that's sort of the only thing it can be dividable. You will only have 1 node physically have them, basically. So the number of mappers, you can specify that values, but that values most time is depends on how many input splits it has. The input splits is a Java class as defined in the MapReduce Java libraries. It's not just depend on the size of the data to determine the input splits, and it's also to do with what type of object you are storing in what format. So the number of input splits is joined by the size of your input data, as well as the format how you're storing your input data there. So in the input form, there's quite a few different implementation within the MapReduce for the different input format. So one for one, it could be a line readers where you want to see my data can be divided by per lines. That may give you most number of the input splits the Hadoop cluster can generating, but that may not be most efficient way to go. And a lot of times the input splits, it could be determined by the number of blocks you are actually used to store your data. So if you just have 1 GB of data and with say 128 megabytes of the block size, then you have this number of the block. But your data being distributed in this number of blocks, that number will be sort of the maximum number of mappers you could generate. On the other hand, if your data has become 1 terabytes, then you will have 1,000 more times of the input splits with the same kind of storage format there. So that is decided what's the sort of maximum mapper process you could have. So other than if you're eventually dealing with the data bigger enough, then you are always going to have enough input split. Then it also going to be limited by the actual computational resources your Hadoop cluster has. And then there's a lot of settings inside the yarn where they can specify what's a minimum size per map task can run. And then your map process will be limited by that size. So if your yarn decided and for the 10 nodes, I can only generating maximum 100 map tasks. If you give 200 map tasks, even you have 2,000 blocks and 2,000 input split, you'll still only be able to just run, say, 10 of those map process there. So on the reducer side, it's more or less a computational dependent values there. On one hand, it processes the output of your MapReduce process, right? So your MapReduce process, the key value pair is generating is going to be through the partitioners. Your partitioner will partitioning based on your how you implementing the partitioner into different groups there. Assuming that you always can partitioning enough groups out, then the partitioners will decide how many number of groups to be generated based on the number of reducer you are specifying. So in most cases, you may feel you have more control over number of reducer. You gave 1,000, it may try to generating 1,000 reducers. If you give 10, it may just generating 10 reducers. That in a way, you are telling how many groups the partitioning process will generating for you. In the case that say if you tell him I want to 10,000 reducers, but your partitioning, whatever the implementation or with your data can only generating, say there's only 10 unique keys out there, so you cannot have 10,000 partition. You do not have 10,000 groups, then you will end up with 10 reducers in that case. So when the number of group is not concerned here, then most time the reducer will be determined by the actual resources you may have. The resources in the Hadoop world is typically named as a container. So each containers can run 1 map task or 1 reduce task. The number of reducers is typically be a variable along how many maximum number of containers your cluster can generate into use. There are actually 2 different ideas about how that correlation with it to the number of containers. So the typical suggestions I saw in the practice is some people suggesting you could have a 0.95, so which is a number very close to maximum number of containers you may have. So what does that mean is you want the Hadoop cluster to generating all the reduced process and do that as one pass. So you can have all of them have all of the reducer run concurrently. That's sort of one idea. And the other idea is actually saying it may be better to generating 1.75 times number of reducers than your maximum number of containers. So guess what will happen when you do this specifications? See, the maximum number of available containers that decided how many reduced tasks it can run at the same time, right? So if your reduced task if you have 100 reducers, you have 100 maximum containers, and now you are saying I want 175 reducer. What happens? The Hadoop cluster will only be able to run first 100 of reducers for you. However, some of them may finish quicker, some may finish later. So they will running the other one in the once one container is free, they will give another reducer task to it. So the idea behind using a larger number than your available containers is actually if you're expecting a load balancing to be an issue, meaning partitioning generating some group much larger than some other groups, then this way it maybe helps you to do the word balancing, like where if some reducer working on a smaller groups, then they can work on other groups quicker. Okay, so both of the ideas is out there, and it's again it became to a workload dependent thing. So you want to know more about what exactly the group size it is, and whether there's balancing could be an issue or not. Okay, that is about the basic concepts I want to introduce with the map and reduce. So I hope that gave you at least some ideas about what MapReduce code looks like and how you may be able to work on them. The other part of the lecture for the first session is I want to introduce basically the concept of Hadoop ecosystem. So, so earlier on the presentation, I mentioned that the Hadoop is initially just a open source implementation of these nice programming models. But now it's being used very popularly commercially in almost all the big company you can think of. They have some version of Hadoop clusters and use it for some of the processing capabilities in the backend there. Like I know like Twitter, Netflix, Facebook, they all have something equivalent to this and they are using them. So they are now just using the MapReduce on HDFS alone, but there are also a lot of other projects that has been developed and can be run on top of Hadoop that can help people to managing those data and to do the analysis quickly. On here, we do not have all the support. We do not support all of those projects, but if you do have a particular needs on certain project, just feel free to let us know, and we may consider to install that or make that one available for your analysis needs there. We do supporting some of them. So out of these pictures, just quickly, the Mahout is the logo is this small elephants and a man sitting on them. So Mahout is a word for that elephant riders. I think the idea is based on say the Hadoop is this big elephants. The Mahout is how you can really use them in an easier way. So it's a high performance machine learning libraries where they have a lot of implementation already being implemented. It probably the best use if you're developing your own code and you want to using some existing implementation for the algorithm for implementation. But on the other hand, some of those implementation is also available as a standalone command line options where you can just invoke them through Mahout, then based on that program options. We will go through some examples in the next sessions about that. That's one thing I will introduce, and the couple of other things people use the very commonly, and I'm not going to spend a lot of time on them. Is one is HBase, and one is a Hive. So some more details about the Mahout is already mentioned. It's a machine learning libraries for the Hadoops, and it has a lot of the algorithms already implemented in there. So it's grouping it. If you look at the documentations on Mahout, it will list them by different categories. So here's sort of top categories of algorithm that already implemented. Yes?
I had a question online if Spark was going to be supported.
Yes, we're supporting Spark. So during the exercise, and I will show you 2 slides about Spark as well. So, but for these trainings, we are going to primarily focusing on how you can, what's a Hadoop it is, and how you can run things with Hadoop. In the future, we may have a separate trainings on how you may be able, more specifically on the Spark, and how you run them. Any other questions about other? So if you have any particular tools or project in mind you want to use, or you feel it's useful, and even you do not you just heard about them from somewhere else, you want us to make that available, just feel free to let us know. So the Mahout has a lot of the data mining algorithm already implemented in there, and all those algorithms runs under the MapReduce models. The other features is not showing up in Hadoop ecosystems, but it's became very useful and popular nowadays. It's called Hadoop streaming. So for today's introductions, I will do some more. We will emphasize more on the Mahout and the Hadoop streamings. And in the exercise, there are also some example things you may do with both of them. So for the Hadoop streamings, the goal of the Hadoop streaming is to enable people to run a MapReduce jobs and with other language as well. So the other language could be Python, could be Perl, or could be R, or any your favorite programming language. You write something, as long as it meets certain input-output requirements, there's a chance you may be able to use that directly with your Hadoop streaming features. So in this case, so in the previous example, in the WordCount case, what I showed you is one Java file, which including implementation in Java on what the mapper class should be and what the reducer class should be. So in the Hadoop streaming, it's doing the same map and reduce process, but in this case, you do not need to have to write or developing a Java code for that, but you can using other language to implementing same map function and the same streaming, same reduce functions and pass that to the Hadoop streaming API there. Let me try to stop this so I can show. Some reason it's the formatting is messed up when I go to the full screen mode. So I'm just going to show this one, then I will go back to the full screen mode. It's so this is sort of the basic API of the Hadoop streaming. So you can use it as a separate, it is available as a separate jar files, and you can run them as if you are running any other Hadoop applications. But just in this case, you're running these Hadoop streaming applications, and the input parameters allow you to specify what processing routines you want to use as a mapper process for this, and what's a reduce process you want to use for this, and where are your code it is, and how you can run those codes in there. So the rest is just standard input, output, and map and reducers. So for the Hadoop streamings, it's really powerful, and it allows you to take advantage of the MapReduce programming model. At the same time, you don't need to learn Java if you're not already a Java developers. Just to run through some examples, I will show a very simple examples. You can even do the same word count processings. Instead of implementing them in Java, you can actually implementing them just with the bash scripts that you can do the same mapper, same same reducer routines. So let me go back to the full screen mode. So I have this example code available, so later you can actually checking them out to take a look of those. So this is purely written in bash scripts. How many of you are familiar with the bash scripts? Okay, actually more than people familiar with the parallel computations. You can try it. I'm not really that expert in terms of bash scripts, but this is very simple to understand, and you basically just read a line from your standard in. So once you read that lines, you can splitting that based on per word, and then once you're splitting per word, and then you can just output that back to standard out and as the term and then the value of 1, right? So that essentially is exactly it is exactly same thing with what we did with the Java implementation, where you take input as a key value pair or a line, you splitting them out, and then output you write to specific places. But in this case, that context sort of the standard out. So you run this, and then you get the standard out. You can run this separately with any text files. You can see the output. And then the reduce code in the bash scripts is very similar to the Java code implementations. So you basically you are going to read in two values in here. So the two values is going to be, one is going to be using as a key and using as the values. So this is slightly different than the interface you will have. I showed previously with the Java implementation, where your reducer input will be one key and a list of the values already. But here you're going to get in a list of key that's sorted. You're going to get in a list of key value pairs, but that already sorted based on the key. So all the values with the same key that will come sequentially to you, but they should be one after the others. So that's what the code does. Is to say they will reading that terms. If that term is currently is a thing you're counting on, it's just doing the count for that terms until the term change. You know you are changing to a different keys. So as a result of that, you are also going to just output the key and then you're counting back as your output there. So this is a reduced code implementing in Bash. There's actually a lot of other ways. This is not most efficient way to implementing these kind of things. So if you're familiar with the Bash and you're really like Bash gurus, I'm sure there's a way you can improve this and to make it more efficient. But just to give you some ideas, when you're putting them together, and you can just give that Bash scripts as your microprocess. So I'm just going to using these scripts as my microprocess, and using these scripts as my reducer process. And you run through with the Hadoop streaming, it can actually run. It can actually give you the result there. So you can check out them later. So here I also specify the MapReduce task and MapReduce task here. Another interesting thing you could do is I will show you how you can run both word count in Java implementation and in Bash implementation. You can change the map task and reduce task you're going to use and to see what's the effect on them. Then let me know what do you think and tell me why they are different. So the Hadoop streaming, that is just a very simple example. There's a lot of limitation with the Hadoop streamings and mostly related to how efficiently it can actually does. The code I'm showing you, although it looks really simple, but on the other hand, it doesn't really give you very good performance. When you're doing the practice, I suggest you try it on the smaller data file first, where you see it's finished quickly. But once you're increasing the size, you will feel it's significantly slower than a native Java implementations. But still, the Hadoop streaming is a very powerful and easier way to allow people to take advantage of the Hadoop clusters with your existing analysis routines. So we are actually, in part of our sort of preliminary work here, we actually investigated a example application that implemented and published early on in the field of informatics. In this processing flow, they using the Hadoop clusters to do a sequence analysis. Both are sequence analysis are a combination of the Perl scripts and some compiled C code. What they using Hadoop cluster for is they put in the data inside the HDFI system to let the HDFI system to partitioning through the input sequence file. And then the map process is really implementing the Perl scripts to running some other, running another commonly used sequence analysis tools called Bowtie. Then the streaming will call your Perl scripts. The Perl scripts will eventually call the Bowties and other analysis executables to do the processing. So in this process, it allows the researchers to easily take advantage of existing Hadoop clusters with their existing code they use for sequential analysis and to do analysis that cannot be done if you just have one machines. Okay, so we have some interesting testing results with this. I'm showing, but it's taken a lot of trouble to setting them up as a system installation. So if you are seeing there's something that you maybe actually use for your research, you can let us know. We can make that one available to you. But right now, it's only existed in my home directory, so I can run them to do the testing there. Any questions about Hadoop streaming and the Hadoop concept series? So that's about what I want to introduce as sort of the basic concept with MapReduce. So if you're new to the Hadoop world and new to this Hadoop programming here, the take-home lessons is really the MapReduce is trying to take away a lot of things you typically need to consider when you're trying to do a distributed computation. And for the code I'm showing you here, nothing really require you to sync distributions, sync parallel at all. So you're just implementing them as if you just do a single thread processing. On the other hand, it's taking a lot of, it's do that things for you. So it makes things easier. So, and also even if you're not Java developers and you're just, as a researcher, you want to use it to analyzing large scale data, you're familiar with some other language, or you have a set of tools that already can meet your needs, you just need to scaling the computation up for larger set of data, then Hadoop streaming may be a viable options for you to quickly scaling things up, okay? So how you can try the Hadoop clusters. The Hadoop cluster, because it is scaling out, so you can actually download Hadoop jar files, install it on your laptop, regardless what laptop you have. As long as it can run Java, it can run a pseudo Hadoop cluster or single node Hadoop cluster on your code. So if you want to do some development or want to learn more about Hadoop clusters, I definitely recommend you do that so you can do a lot of code development with your laptop. Once it's working on your laptop with whatever the Hadoop implementation you have there, they can run with any other Hadoop clusters. You can, if you have a bunch of the old machine lying around at home, it's actually not that hard to connecting them together to setting up a small Hadoop cluster at home just with the old machines. Hadoop cluster, the whole Hadoop implementation doesn't require high-end hardware at all. It doesn't assuming you have high-end hardware. It even doesn't assuming you have same hardware. You can even mix probably the Mac Windows together and to build your Hadoop cluster. As long as everyone can run Java, can have an Ethernet connection to the other, there's a way we can make that one working. There's a lot of commercial cloud service providers that offer the services where you can buy from the EC2 from Amazon, and you can buy some balance there, and then you can let the EC2 spinning up a Hadoop cluster for you. You can specify what kind of instance you want and what type of resources there. So at the very last is you can certainly run the Hadoop or testing Hadoop with our resources. So that's going to be the next sessions of these trainings. So with that, let's taking 10-15 minutes break. Then if you have more questions, feel free to let me know so I can answer them during the break. If there's more online people, they didn't catch up with the questions, then it's a good time to ask questions as well.
Just shoot me an email.
Yeah, I mean, if I can just have this issue with that's also fine. So, yeah.
So I think I already unmute. Right?
You are unmuted, yes, sir.
Okay, so let's continue with our second session. So during the second sessions, I will first go through the resources we have at TAG that can support people running Hadoop-based analysis. And we are going to primarily focus on using the Wrangler for today for creating the Hadoop clusters and running some example on the Hadoop clusters. I will run through some examples on how you can get access to them, and once you get access on it, and what are the things you can do, and how you can explore, and some common commands there. And then hopefully we can have about like 30 minutes or so time, so you can freely explore the clusters and to see how it works. So the Hadoop support at TAG, and we actually have 2 clusters can supporting that. So one of the slightly older one we had from last year is a sort of more like a traditional Hadoop cluster that with the 64 Hadoop data nodes available, and each one has about 20 cores. And each is each with a 128 gigabytes memory, and each node have a 16 terabytes size disk in there. So this is a spinning disk-based Hadoop clusters, and it is strictly just the typical Hadoop clusters, and you may heard of or you may have experience with. So we have a 1 login node and 2 name nodes. For that clusters, and it is not a exceed resources, but if you're interested to use it, you can drop us a line, and we can try to see if we can get you access to the rest as well. The other cluster we currently have is our latest cluster to supporting data-intensive analysis. It's called Wrangler. So Wrangler is part of the exceed resources as well. The Wrangler is different than the traditional HPC in the sense the storage is not really local to the compute node. It's still, we have a separate storage device and a computational device. But on the other hand, Wrangler is also different than your traditional HPC process. Just in the storage system we have separately is not typical spinning disk-based system, but it's a very high performance flash-based system here. So the flash-based system in this graph is showed as this sort of little green box here. It's being direct attached through the PCI interface to each of the nodes directly. So even if they are physically being occupying the 2 physical locations, not within 1 node, but the connection is quite fast. And if you considering PCIe connections between them, and they are not much different, being they are local to that computational nodes. So that's sort of the hardware basis that how we are able to use these technologies to supporting the Hadoop type of the cluster creation and running and supporting people running analysis on top of it. So the Wrangler is a different it's a different than the traditional HPC cluster. So it also has a different kind of usage model we have. So I will spending some time to more focus on the Hadoop clusters, how you can use them with Wranglers. The Wrangler also supporting a lot of other data-oriented services, like you can setting up a database services and to serve or archive your data. So if you're interested in that, we will have a different training sessions in the future days and about those data management aspect of the using Wranglers. So for the Hadoop clusters, and the Wrangler can support user to submitting requests and to create a Hadoop cluster specifically for their research group to use. The Hadoop cluster could be including anywhere from 2 nodes to over 40 nodes in that Hadoop clusters. So once you're requesting a Hadoop cluster, each node will have access to 4 terabytes of the flash storage devices that on this high performance storage system there. So if you have, and one of the node in your Hadoop cluster is going to be used as a service node to run the name node and to run the resource managers. So the actual distributed file system will be 4 times the number of nodes you requested minus 1. And if you have been using the HPC resource like Stampede before, you know you need to submitting a job and to run you submitting a request to request certain nodes and for a certain amount of time and to run your analysis. It's a similar process here, but in the Stampede or in a typical HPC clusters, the time you can use that machine is limited. Usually it's like 48 hours or some is even just 24 hours. But on Wrangler, what we support is called sort of data analysis campaign, where you can request a Hadoop cluster for say 1 day or up to 30 days. So on that 30 days, you will have access to that Hadoop cluster. That Hadoop cluster will be up running for that entire 30 days of the time. So you can have enough time to importing your data into the HDFS or getting a large data available for your analysis and do an analysis and getting your data off at the end of your allocations. So for today's trainings, we are going to focus on how you can using the Hadoop kind of support on Wranglers. So to get started with Hadoop on Wrangler, it's really a 2-step process. Step 1 is you need to submitting a Hadoop reservation request, which is basically tell us you need a Hadoop clusters and for your research project. And then step 2 is once you have your reservation work active and running, and that process will also just starting the Hadoop cluster for you automatically, then you can have access to that Hadoop clusters there. For today's practice, you don't need to worry about step 1, so you don't really need to create Hadoop reservation because we already created Hadoop reservation, so everyone sign up for the training will have the access to that Hadoop clusters we already prepared and created, so you do not need to go through the reservation process. But nevertheless, I will go through that process. So in the future date, if you are interested to use Wrangler for that, so you know how to do that reservations. So to create Hadoop reservations, and we have Wrangler web portal to do that. So you only need web browser access and to submitting requests through there. So once you're submitting the access through the web portals, once your Hadoop cluster is up running, you would need a secure shell client be able to access the Hadoop clusters that running on the Wranglers. You may also want to have a VNC client, which can starting a VNC server on one of the Hadoop nodes, so you can see some graphics or do some interactive analysis there. But the VNC client is a optional features you don't have to have. So let me start with a walkthrough on how a Hadoop reservation being created. So we have setting up a data portal for the Wrangler for people to use Wrangler to submitting the reservations. It's the web address is a portal.wrangler.tech.utexas.edu. Once in there, you see the login interface. You can choose either using your tech portal user account or using your Exceed portal user account. This is tied to which allocations, which username your associate has actual allocation on the Wrangler. So if your allocations through the tech user portal have the allocation, then you probably only can log in through the tech portal account. On the other hand, if you're having Exceed allocations, then you probably have to use your Exceed credential to log in theirs. If you have problems to log into the portal right now, it doesn't really matter because we are not really need you to do anything with the portal at the moment. If you could log into the web portal, feel free to log in there, and so you can follow better to know what I was referring to and what I was talking about. So once you are able, if you can log in to there, for the first things you will see is sort of a dashboard view where they list your available allocations and that you have on the Wranglers. If you can log in now, you should be able to see at least you will have at least one allocation listed in theirs. So at the end of that allocate, at the right hand of that allocation, there is a button called manage that allocation. So if you click that manage allocation buttons, then it will take you to another page called create reservations. On that page, you will see you can create a Hadoop reservations, or you can create a non-Hadoop reservations. Just be able to using the flash devices, flash storage as normal Linux file systems, or you can create a reservation with a database there. If you have any questions regarding to the portal you're seeing, or you have problems, feel free to let us know. And if something easier, we may be able to solve now, so you can log into it and to see the interface. So eventually, it should be just a 2-click away once you log in to get you to this page where you can create the Hadoop reservations. So to create the Hadoop reservation, there is really just 3 things you need to tell us. One is how many nodes you want to have. The default, the number of nodes is actually should be 2 to 10 nodes. So we want the Hadoop class should have at the minimum 2 nodes. So you can have one as a name node and the other one as the data nodes. The default requirements in there is you can have up to 10 nodes, but if you feel you need a much bigger Hadoop clusters, just file a ticket. We will take a look at your case to see if we can create a much larger Hadoop cluster for you in shorter amount of times, or your work may be better done on things like raster for longer durations. The other things you need to input is durations of your Hadoop cluster should be up running. On the Wranglers, and the duration is not being charged by CPU hours, but rather is charged by days. So the range of the duration you may choose from is from 1 day to up to 30 days. At the end of the 30 days, your reservation will be expired, and at that time, when your reservation expires, your Hadoop clusters will also be shutting down, and whatever the data stored in Hadoop clusters will be deleted at that point. So you need to keep that in mind, and to make sure you get your valuable data or your results off the Hadoop clusters before the reservation runs out. The third input you need to give us is a start time. So in here you have a choice to start as soon as possible. So then what the system will do is looking into the number of nodes you're requesting and the time you're requesting, and to decide the latest dates, and that we can start in that Hadoop reservation for you. It could be next hour, or it could be next day. It depends on the system usage at the time. Or you can trying to schedule it as a time. Say I want to this Hadoop cluster for me next week or next month, so I can run some analysis to catch certain deadline. Once you're ready for that, and you click the submit buttons, and it will be turned to the system will first try to make the reservation. You will see a web page like this, and where you see your current reservation request, how many nodes you're requesting, and what's the start date you're requesting with, and how long it is, and who requested. From here, that's pretty much all the information you can see from here. And from the portal, if you change your mind and you do not need for that time, or you find some parameters wrong, you can actually cancel out the reservation before it goes to active. So a little bit more about your Hadoop reservation on Wrangler is, so we do the Hadoop reservation for each project. So right now, it's kind of limited. Each project only can have one Hadoop reservation going on at the same time. So we would rather you have a, say, 10 node Hadoop reservation rather than you have 2 people in the group to starting 2 5 nodes Hadoop reservation at the same time. Anyone in the project currently can submitting the Hadoop reservation request. It doesn't have to be PI to submitting that request, but once you're submitting that Hadoop request, once the Hadoop is up running, all the peoples in the project can also access to that Hadoop reservation as well. And then during the request, you see, like, we ask you, say, how many nodes instead of how many core you need, and we ask you how many days you need instead of how many hours you need is because in the Hadoop, in the Wrangler, we do not charging your allocation by the core hours that you are charged on other HPC machine like StampP. So you may notice if you have a allocation on Wrangler, it's a much smaller number than you have on StampP. So if you can log on to there, you can see the project I'm adding you is only like have 5,000 ICU there. Because each ICU in the Wrangler is meant 1 node hour, regardless of how many cores in that node. As long as you require 1 node for 1 hour, that's 1 ICU. So for example, the Hadoop reservation require the minimum Hadoop reservation for 2 nodes and 1 day, that will cost you like 48 ICUs in that sense. And also keep in mind that how many data you expected to do the processing there. So in the Hadoop reservation page, this is the parameters you have to input. You may not see clearly through the slides, but in the page, we have some guidelines to help you to estimate. Say if you have a certain amount of data, and then there may be a certain amount of a minimum number of nodes of Hadoop cluster you need. So just keep that in mind and be sure you requesting the Hadoop reservation that has enough storage for your analysis needs. So once you're submitting the Hadoop reservation request, you will come to this check reservation status page. On the web portals, you can see the reservation status. It's going to be either pending, meaning they are still not really running yet, or it's going to be active, which means they're running. And sometimes you may see some error message. It's because we cannot schedule that for that time. But if you want to know more information, when you actually log on to the Wranglers, you can using a slurm command to getting much more detailed information about your Hadoop reservations. So that's also bring to our next topic on the step 2, how you can accessing the Hadoop cluster you created on the Wranglers. So for this part, you would need to require to have a secure shell client to do that connections. If you have been running jobs on the StampP, you know what the SSH client is, and you probably already have access to it. So I'm not going to spend a lot of time here. But if you're completely new to here, you can just Google secure shell client, and there's a lot of the free or open source version of the secure shell client available. You can for both Linux and the Windows, and for the Linux and the Mac, you actually do not need to install anything separately. You can use in the built-in terminal to do as a secure shell client. For Windows, there's a command line interface. There are also a lot of GUI interfaces. So regardless which client you're using, you eventually will end up by connecting to Wrangler using either the SSH to Wrangler, or you have some GUI interface, you do a new connection, and put Wrangler in there. There are also a couple of things new to us here. Right now, we're using a 2-factor authentication. So if you have an Exceed account, that's probably not a big issue for you. So you can using the single sign-on features of the Exceed to log on to the Wranglers. But if you do not have the Exceed account and you just have a local tech user account, you may have to have a TOEFL authentication setting up in order to be able to connecting to the Wranglers. This is just a one-time setting up process. If you're local, if you're working at UT, you're probably setting up for your UT ID already. That probably works here as well. So we have on the course webpage, we're posting the same slides, and then the URL is available. You can click on URL to see more instruction about how to getting that access and how to get that TOEFL authentication done. Feel free to try to getting that one done now if you are having trouble with it. If by the time we're ready to do the hands-on exercise, you are still cannot accessing to the Wrangler, feel free to let us know so we can help you out with it. So on the Wranglers, Wrangler is on one hand is similar to the existing HPC cluster we have. So it does has long-term file systems on Wranglers. So when you first log into the Wrangler, it will be default into your home directory or your home file system. So the file path will start with /home, then some weird numbers, then your login name. This one has a small quota, so you may not be able to put a lot of data in there, especially if you expect to work on large scale data analysis. You do not want to put all your data inside your home directory. We have two other file systems for you to use on Wrangler. One is a /work file systems. The /work file system is globally mounted across all the resources we have at tag. So, which means you can access /work file system from Wranglers. You can also access /work file system from Stampede or from Maverick if you have allocation on theirs. If you have allocation on there, you probably know what that means. If you do not have them, you will see the convenience when you have the allocation in the futures. In addition to /work file system, the /work file system, since it's a global mounted and shared among all the resources, there are also a 1 terabyte quota for each users on the /work file system. It may be quickly run out if you're doing data-intensive research for that. So on the Wrangler, we also have another spinning disk-based file system called mounted at the /data, where it's for you to really staging the very large scale of the data file, like multi-terabytes of the data there. So if you're doing a Hadoop analysis and you can putting your data into /data file system first, then once your Hadoop cluster up running, you may need to importing that from /data file system into the HDFS system that created by your Hadoop clusters. So that's some basic things about Wrangler's file system there. So go back to the Hadoop reservation. It's once you are done with your portal page and you do the Hadoop reservation you created, it shows up. It's in there, and then you can log on to the Wranglers. You don't need to. You can, once you have the allocation on the Wranglers, you can log on to the Wranglers anytime. It doesn't have to be, you have to have reservation active to be able to log on to it. So once you log on to the login node of the Wrangler nodes, you can using the as control show reservation to show the current reservation you have. This is a screenshot I took for the previous lectures. So it's a different reservation. It's not the one we are currently have. The main things from the information can show you is the reservation name shows up at the first field. You will be using the reservation name in a few other places, so you may need to know what reservation your current Hadoop clusters is up running there. For this case, for this screenshot, it's a test allocation that I created. If you're creating the reservations through the web portals, the reservation name is always to be start with the Hadoop as a prefix, then followed by your allocation project in the exceed, so you know which allocation is yours, and then some numbers. It's just we are keep tracking sequentially how many Hadoop reservation it takes. So that gave also the uniqueness of the Hadoop reservation names. The other way you can distinguish if there's multiple reservation to see which reservation is the one you have access to is there's also the list of users that have access to that reservations. It also shows information like how many nodes you're requesting, when the Hadoop cluster will start, and when the Hadoop cluster is going to be end. We do have some user had a comments on here. You can see the start time. The time is a default to Central Daylight Time. That's where tax time zone it is. So if you're on the West Coast and the East Coast, this time will not adjust on your local time zone. So you have to adjust yourself. So you may do some expectation. Say here, if you're on the East Coast, it's 11 o'clock. You feel like you have 1 hour left, but it's may actually already trying to decommission that Hadoop cluster for you already. So in the future, we may trying to do something here, but it's an output from Slurm command, so it's very hard to localize into for each users. And also the other important information you can get from this this information is you will see a list of nodes that are going to be used to create your Hadoop reservations, and you want to know the first nodes in that appear in that list. Usually is the nodes with the smallest number, because that's node, the first node in the reservation will always be used as a service node to run the name node on, to run the service name node on. And that name node may be used in a few other features when you're actually using the Hadoop clusters when you need it. So, and also the Hadoop cluster, it will starting automatically at the beginning of your reservation. So we have a set of scripts that can automate the process. The Hadoop cluster will start with a set of default settings that's specified in that starting up scripts. We have some of the default settings being specified through the user documents. If you want to know some particular settings, you can, once it's running, there's a Hadoop command you can get in the configuration settings. If you need to override some settings, the Hadoop cluster allow you to override most of the settings dynamically when you're using them. When you're running a Hadoop command or when you're running the application, you may be able to adjust a lot of the settings dynamically that way for that particular application you're trying to run. There are also some Hadoop cluster settings that cannot be adjusted that way. So if that happens to be something you require and it's not matched to what we are creating, you just let us know, so we may be able to modify that for you or restart the Hadoop cluster for you upon your request. The last thing about the reservation is the last field is a status. It's called state. So if the state is equals active, it's meaning your reservation is now up running. So once your Hadoop reservation is up running, there's several ways you can access that Hadoop clusters in the backend, but all of them require some form of a Slurm job. But in this sense, the Slurm job is just trying to assign one node from your Hadoop cluster so you can have access to it. We are not going to charging separately. As you already charged by the time when you are reserved the Hadoop reservation. So the Slurm job you submit against that reservation will not incur any more ICO charge on there. So even you submitting like 10 minutes jobs there, they are not going to charge you another one ICO for that. There are 3 different ways you could access the Hadoop cluster once it's up running. One is you can start in a VNC jobs. We have a sample scripts available for you to use. The VNC job, the biggest advantage of starting the VNC job is you can actually log on to one of the nodes with GUI interface. That will grant you access to say the web user interface or web API of the Hadoop cluster if that is something you need. And also you can gain some graphic output if your analysis has other features or you need some graphic or visualization features to go with your Hadoop cluster as well. For most usage, we would like to suggest you starting a iDive job. So iDive job is very easy to start, and it will assign one node from Hadoop cluster to you. And what you will get is just a console interface, but that's most time is enough for you to say just testing out your code or transfer data in and out Hadoop, or submitting a Hadoop job through that console interface. The last way is more or less the traditional way how you can access in the cluster is to submitting a Slurm job where you can put in your Hadoop application as executable inside that job scripts. It can run automatically with the Yarn resource manager in your Hadoop clusters. So just keep in mind that the purpose of the Slurm job is to give you access to the node. So once you have the access node, if you're going to running analysis, you are going to submitting that analysis to the resource manager of the Hadoop clusters again. So it doesn't matter how long your Slurm job lasts. once you put the Hadoop jar certain command back to the Hadoop clusters, it will run inside the yarn. So you can immediately quit, but your job will still running in the yarn. So you can, if you're expecting your job to run for 2 days, you can submitting, say, a 20 minutes iDive job, just submitting, initializing the analysis process. You can log out, then you can say checking back a day later by logging into it, then you can through the yarn to checking your job status there. So we already created one Hadoop cluster for use. I will first go through how you can accessing class through the VNC sessions and to give you some basic concept about Slurm job scripts. That's going to be a similar script you're going to use if you're just submitting a batch job. But for the exercise, if you don't have to check out the VNC sessions for today, we would recommend you just stay with the iDive job. It's much shorter and easier to start. So the VNC sessions, we have a sample job script for you to use at the share doc and slurmjob.vnc. So if you want to use it, and you need to copy that into your home directory so you can make modification to it. It's a text file. If you're not very familiar with the Slurm job submissions, I'm highlighting the things you really need to change here. So on the top, there are some like disclaimers and what this file is about, blah, blah, blah. It's just comment lines. And then at the bottom, there's a lot of more lines, but you notice there's you normally shouldn't need to edit anything beyond that. So do not edit anything beyond that. That may break how the scripting works. So for the VNC jobs, the only thing you need to worry about is the one that in this sort of the bracket we highlighting out. I'm highlighting like 3 different color codes. So the right one is something you have to change. That's specify which allocation you are going to use. So I put them as a default allocation we have, but you may not have them. So you need to change that to whatever allocation you have there. The yellow one is a sort of the optional things you don't have to change. It just specify what output file it is and where you see the output. The blue one are something there, and you don't need to change either. So you only need to, you're always going to submit into the Hadoop queue. And you are always going to just, you are always only need to requesting 1 node, so you don't need more than 1 node for the Hadoop clusters. The number of the MPI tasks is irrelevant in this sense at all, so you can totally ignore that line at all. The other things you may want to adjust dynamically is the one I left over here. It's a request of runtime of your VNC sessions. So just keep in mind the time you're requesting. It doesn't have to equal the time your analysis to run. You can just use it to quickly pick through the Hadoop cluster status, submitting your job and do some interactive analysis, then be done with it. So you don't really need a very long time for that either. So once you make your Hadoop reservation scripts ready, and you can using SBatch to submitting that job scripts. For the Hadoop reservation, you have to specify which reservation you use. So in this previous example, my reservation name is Hadoop test 8. So I need using this dash reservation equals Hadoop dash test 8 as my command in the command line. So this dash reservation can also be the option you can insert into your Slurm file. So you can, if you're having a Hadoop cluster running over 30 days, you don't need to input in the reservation every time. You can just run, if you put in that one inside the job scripts, it will, you don't need to put that through the command line separately. So once you're submitting this job, you will see some information about this job being submitted. Then once it's that one done, you can monitoring that job status by do tail VNC server.out. Once it's setting up and up running correctly, you would expecting something, some input like this, some output like this. So here on the last 3 lines, it's actually the very crucial information for you to get access to the VNC sessions created in the Hadoop clusters. Just to follow exactly what we're doing here. The first line, do a secure shell autonomy through your computers to the login nodes, and then you can accessing them through a VNC client by connecting to your local port. One of the main features that or the needs you may want to accessing through the Wednesday session is be able to see graphic output, because all the compute node is a firewall behind the public access. So the only way you can accessing the web interface of Hadoop clusters to do the management stuff is through the Wednesday sessions. Once inside the Wednesday sessions, it's basically like a remote desktop. So you can start in web browsers, and you can specify your name node address, and where there are 3 types of information you could see. So here is a name node page where it shows the overview of your Hadoop cluster, how many nodes in there, how big the distributed storage it has. And the other page is actually shows your current running job. So that is where you can see who else was running the job there and how long it has been running. You can do similar things through a command line. The web interface doesn't give you more than that. It just give you a nice and easier to navigate option to see all those applications. From the applications, and you can also click and accessing to another information they provide called the job histories, where you can actually from there to see each job, whether it's finished successfully, some overall job status, and how they have a link to connecting to the log file, but that one may actually not working through the web interface. You have to do that separately through the command line interface. So that's about the Hadoop reservation through the Wednesday sessions. If you are interested, feel free to start one. The other thing with the Wednesday session is that if this is the first time you're running them, you would need to setting up Wednesday password. So you will see that instruction when you try to run in that JavaScript. For today's exercise, and we would recommend everyone just starting the iDive sessions. So the iDive is just this command line tools. You can submit a request to requesting a interactive sessions from the one node. To run it, you just do iDive, then using -r, then specify which reservation name you want to use. Then it will generating some output for you. Once it's done, you should see your login has changed from the login to some of the nodes, something like C252 and some numbers. So that means you are already on one of the nodes inside the Hadoop reservations. So for the iDive sessions, you can just run as simple as just iDive followed by your reservation name. Even you do not give the reservation name, the iDive will actually ask you whether you want to use that reservation or not. So it's very simple to use. It starts with a set of the default options. You can using -A to override the default allocation name that being used for that project. That has to be matched to the allocation used to create the reservations. So if you have multiple reservations, and you may need to change that in order to get the correct access. The other common option would be this -m, which is specify how long you want your iDive session to be lasted. So the default is 30 minutes. That would be enough for you to submitting the Hadoop command to it. But if you need longer, you can using -m options and to getting longer time. So the reason we want you to requesting a node, it doesn't really matter whether you are requesting the name node or any node in the data node, any data nodes from your Hadoop cluster. Once you are in any of those nodes, either through the iDive or through the Wednesday sessions, you basically can run any Hadoop command. All the Hadoop command or Yarn command you run will be submitted to the Yarn resource managers are being run under the entire cluster. So which node you are currently on, it doesn't really matter with what node you can, what things you can do. So if you are new to the Hadoop and the Hadoop file systems, the Hadoop cluster is a separate file system than your local file systems, and it's different than the Linux file system as well. So it's a separate file system shell. It's a lot of similar to your typical Linux file systems. You need to invoke that file system shell command. You need to start with the Hadoop and fs. That's actually calling a jar file with for that file system to supporting those functions. So after that, and a lot of command you may feel similar to your normal Linux command, like the -ls is to list your directory file directories. It's doing the same thing here. some of the parameter you can give, you typically use with your Linux command, are also supported when you use it through the Hadoop file system as well. You can, once you are inside the Hadoop HDFS there, if you want to follow along, you can feel free to log on to the Wrangler clusters, and you can start in the IDAP sessions and just to see if you can get one. So once you get one, get IDAP sessions, you will be assigned to one of those nodes, and once you are in there, you can run this particular command, hadoop fs-ls. So that's listing the directories. The slash is just it's the same meaning like listing the root directories. If you do not give that, it will list your default home directory inside the HDFS as well. So if you do this command, you will see the higher level on what the HDFS file system will be looks like. There are 3 high-level directories. The slash temp is a public writable and public accessible. It's not only used by you can use them, but most time a lot of the Hadoop-based application will use that to write a lot of intermediate files in there. And if they are finished correctly, most time they will be clearing that out. But if they are not finished correctly, you may see a lot of leftover things in the slash temp as the time goes on with your Hadoop cluster. So most time, if it's not associated with any running jobs at the moment, you should be able to clear that directories out. Then the other top level directory is the slash user. So that's equivalent to the slash home we have for the home file system. Each users will have a directory in there. So that directory will by default only accessible by that users. It is followed by slash users and your username there. So that directory is automatically created at the time of the reservation running and based on what are the users being assigned to other reservations. If you are adding to the reservation after the Hadoop class already running, you may not have that home directory. If that's the case, you can just let us know. We can create one for you. The third one is a slash variable. Again, this one is most time is being used by the Hadoop system to store information and by other application. A lot of case is where the log file is being stored in there. You can pull those log files out through the command, or you can directly browsing into the directory and trying to see them. There's a lot of the file system shell command is support. The 2 most important one for you to start is a put and a get. So basically when putting a file system from your local file system inside your HDFS path, and the other one is to getting something inside your HDFS and to back to your local file system here. There's a lot of other file system shell commands available in there, so I really encourage you to explore on your own during the exercise or afterwards. They have a very nice documentation online to specify all the file systems command you can use and how to use them. The other important pieces with your Hadoop clusters is a resource managers. So that is also running at the time your Hadoop cluster running. All the jobs you run inside your Hadoop cluster will go through your Yarn resource managers. Even if you are interested in a Spark, we only support running Spark through the Yarn as a resource manager as well. We do not setting up the Spark standalone model right now. For Yarn, you can using Yarn to submitting job. Most time it's identical. You're using Yarn jar your application, or you're using Hadoop jar your applications. There's a significant less amount of Yarn command you need to concern with, and most Yarn command is mostly for administrative purpose and to see the status. So one of the most important things you want to know is a Yarn for by the application. That basically gives you same view you can see from the web portal information page about what application currently running, what is being queued up. So that's what the default view will show you. You can use in dash list and followed by some option to say, I want to see all the finished job, and you can specify that and to see them. So that's allow you to see not only what's currently running, and if you're submitting anything, you can check your job status that way as well. The other common options you may want to remember is a dash kill. So that's basically if you realize something wrong with your analysis being stuck in at the 10% progress for hours, then you may want to kill it. You can use in dash kill followed by the application ID. The application ID is something when you run the list, it's going to be the first items you will see on the far left. So it's a very long numbers, and you can just copy paste them. Other than the Yarn applications, the other two commands on the Yarn node is basically, it just tells you some status on how many data nodes is currently running. Like if you're requesting 10 nodes, but you only see 5 is running, just you can submit a request and let us know. So we will take a look on what's going on and trying to fix it. Another command is Yarn logs that can help you to gather in the logs for a particular application or logs of the particular container IDs. This is a very valuable and very useful way when you're debugging your code and if something happens there. It is very useful information, but I'm not going to talk too much for today's. And in the future, we may have a more advanced one on how you're developing application, how you're debugging, and how you're profiling. Then we may go back to this command and to go over more details on how the log structures in Hadoop setting up and how you may be able to see the errors and which generating them. Sometimes it's a very painful process. So HDFS and the Yarn is a two major components, like very basic core components with your Hadoop clusters. Those are just some common commands you may be able to use with. So once you're getting to that, then the question is how you can run your first Hadoop applications. So most Hadoop applications is in the form of, say, you have a jar, you have developing Java code, and you compile them as a jar file, then you can run that jar file. You can run that jar file instead of calling Java jar, you normally do with a Java application. You need to either do Hadoop jar or do Yarn jar. So both scripts will do similar things here. It's just jar then followed by your jar name and then whichever class in your jar you want to run, then any parameters associated to that. Another things you can keep in mind is, as I said, you can override a lot of the Hadoop parameters, and that's where you can use in the -d command to do that, and you can give any configuration parameters that Hadoop use. Well, not really any, but most of the parameters, configuration parameters, and then specify what the values you want to use for these particular applications. It's same parameters. The -d can also be used when you're calling Hadoop FS command as well. When you're putting the data, if you want to changing the block size that data for that data file you're trying to import in them, you can specify that when with the file shell as well. So to start with running your Hadoop applications, and you probably do not have a code written now. So the Hadoop comes with a exemplar jar file with a lot of the examples you can run. So word count is one of the example there. I have the command here in the exercise directories. We also have a separate text file and has a command in there. So basically, this command structure is what I was just describing. Say Hadoop jar, then giving where the example jars located. Then you tell them out of this jar file which class or which program you're trying to run. Then you can give, say, number of mappers, number of reducers as the parameters here before you give any parameters to that to be used by your word count class or by your applications. So in these examples, I'm specifying this number of tasks and this number of reduce. And then here's the first pass is the input parameter, input file locations. The next one is where you want to store the output folders. When you start to running them, you would see some online output like this. So that's a standard output the Hadoop generating. It tells you the progress, what's the percentage of mappers is going, what the percentage of reducer is doing. If there's any errors or number of tasks, it's generating. So sometimes, and you may see you can also see information like how many total input splits this particular application can work on. Sometimes you can see some of the job statistic output at the end, say they're generating more map tasks than it's actually needed, and you will see some being killed. So that's another fault tolerant feature with Hadoop. So sometimes they may have a random read and write errors or some memory errors. So Hadoop will automatically kill that map task and restart that map task. the default it will retry it at least 3 times. If all 3 times fails, then maybe something wrong with the HDFI system, so it will fail the entire task. But most time it's you may see some error, but as long as at the end it tells you this job is completed successfully, it means it's completed successfully. It may restart some container a couple of times. That's fine. So doing your exercise, and you can run. So on my examples here, this is a Wikipedia dump. It's available at the /time/data already. I put them in there, but you don't have to directly jump onto that large file. That may taking at least a few minutes for it to finish to run. In the exercise directory, at the very end of the slides, I have some smaller file you can try first. During the exercise, and you can vary in things like, say, the number of the members, number of reducer being used to see how that affect how many actual members, actual reducers going on there. You can see the output files. You can see how many reduce. The choice of your reduce has what impact on the number of output you're getting. So remember what I was saying when I talk about my reduce is that each reduce instance will generating a file separately. So if you just give 1,000 reduce instance, if it runs, you're going to end up with that 1,000 files. You may still need to process and worry about. In the example jars, there are some other example other than the word count you can run. So there's a parallel grep. You can searching for a particular regular expression out of large scale text. You can run them. There's a calculating pi examples. You can just run Hadoop jar with a jar file without giving any option or any command. It will show a valuable option for you. And if you see something interesting, feel free to run that. And if you do not give any parameter, it actually will show the help message on what parameter is required. So that's the basics about how you can start in running your applications there. In the exercise, I also have a section I can show you later, and you can. I have a work on the Java file, that the source Java file in the example folder as well. So you can actually run through the compiling process, packing that in the jar. So that is a similar process you want to go through if you want to run in your own code. The other practice you could do is we have Mahout installed on the Wranglers, so you can at least to go through the process on Mahout. How can you may use Mahout with the algorithm already implemented to do some analysis there. The Mahout has a lot of algorithm being implemented as a library, and the only subset of them that are exposed and or available as a sort of standalone application you could run. So in the next several slides, I gave some very detailed instruction on how you can starting a k-mean clustering on a very well-known common used testing data set in the text mining. You don't have to go through all of the steps. Just a quick list, you can downloading this news data set from this URL. You can, if you want to go through the whole process, you can use a wget to get that compressed file. So that file will including like 20 file in the SGML format. And then the step 1 is actually running that on your local file system and to extracting the content. So the Mahout has a specifically implemented class to extracting the text information from this particular data set to a separate directory. So that directory is on your local file system. After you run this, and then you need to put in that file directories inside the Hadoop file systems. So this is a command I run beforehand. So you already have them in the HDFI system. So if you want to skip the step 1, you can directly start with the step 2. So in the step 2, now at the beginning, what you download is a compressed SGML file. It's a file similar as an XML file. Then after you do the extraction, it became a lot of pure text file. Then the step 2 is actually the Hadoop, the Mahout will converting that into a more efficient, in another more efficient format called sequence format. The sequence format is a comprise the same information, the key value pairs, but rather than being a text file format, which you using a character, it's actually a binary file, so it's more compact, and so you can pack in more information that way. And if you're doing large scale analysis, a large web archive collections, you need to converting that to the sequence file for efficiencies. And a lot of Mahout algorithms only works on top of sequence file as well. So you can now directly working with text file. You can go through the similar process using the sequence directories command to converting a directory, including a lot of text file, into a bunch of the sequence files. Once that, then the step 3 is to creating the vector representation. So that vector representation can be input for data analysis algorithms. In the text minings, that's going to be a term frequency, inverse document frequency vectors eventually. That can be used for clustering, or if you have training data set, that same vector could be used for classification or association analysis. So the step 3 is basically trying to create that vectors. The step 3 is actually going through and create, once it's done, if you log into a directory, it's actually create multiple different vectors. It's a different form. It basically will go through one pass to create a term frequency of all the word occurrence of your text collections, then the document frequency, then calculating the TF-IDF, so on and so forth. So all those directories are already there in the /time/data, so you should be able to access. So you can actually jump in and continue to any of those steps. You don't have to do step 1, 2, 3, 4. You can go directly with the step 4, or even just step 5 will have some result file in there. So if you just want looking at them. So step 4 is your main analysis step, where you run the k-means clustering with Mahout. So it's a similar than with your running Hadoop command, but instead of calling Hadoop jar, you just calling Hadoop, calling Mahout, then followed by the options. Then here's a sort of algorithm-specific parameters you want to give for that analysis you're choosing. The k-means implementations, when you run them, you will actually see it's starting multiple MapReduce jobs. That's because the k-means algorithms is an iterative algorithm. It runs through the multiple iterations. During the break, there was actually a question asking about what are the algorithms best for Mahout type of analysis. There's no universal answers, but actually, but Hadoop is best for those algorithms that doesn't need iterative processing, and it's just a one-pass processing with the same data, and you do not need to sharing your information among your subset data. The more dependency you have with your data, then the more algorithm efforts needed to make that one being running efficiently under the MapReduce processing in general. But still, the efficiency of the MapReduce or the Mahout implementation is not just coming from algorithm implementations, but also coming from whether you have this kind of support for you easily to run them. So it's not just whether it can give you best time, but also how easy you can use something versus you re-implementing everything from the C from scratch. So after you're running the analysis for the clustering result or any other clustering method, you can use cluster dump. So the result will be stored at this output directory, but it's also in the sequence format, which is a binary file. You can use cluster dump to dumping that sequence file result into a readable text file, so you can see what's a cluster centers and how many top frequency terms in that clusterings. This you can just without giving any parameters, you are always going to get a help screens where it shows you what's a parameter for us and how you can use them. So the help screens looks like this: a -- input is a specified input path, and you can see what other options you may have in there. Here's just a quick example on what the output looks like after dumping them into the cluster output files. So on Wranglers, that is for all those processing in the HDFS, the intermediate result is all available at the /time/data, so you can use them. If you want to doing from scratch, that's fine, and we have the source file inside in the exemplar directories as well. you can run the Hadoop streaming package. I do not have slides here, but I have slides in the first sessions. That's essentially what you need to do on the example directories. You will see a text file with the same command again. So I don't need to mention that here. On the Wrangler, we currently also have HBase installed. So if you need to use that as a storage manager for your key value pair, that's doable. HBase is just an open source implementation for Google's big table applications. It's not really a database. It's not really a MapReduce thing. But it's providing fast random lookup for key value pair of your informations. I know a lot of interest into running the Spark. You can run Spark once you have the Hadoop reservations. We only support running Spark through the Yarn, using Yarn as a resource manager, so you can submit your Spark jobs with Hadoop clusters through the Yarn and to getting multiple nodes to run them. If you do not using class mode, the other mode is going to be local mode, where you are only going to run it on the node you are currently on. So, it's a quite big difference. If there's any other tools or package you would like to use, and just feel free to let us know. So here's just a quick example. So once you are on the iDive session, if you are interested in using Spark, say the Spark shell, you can do Spark shell, then giving the master to be using the Yarn cluster. So that's we will starting the Spark shell by using the Yarn as a resource manager. So anything interactive things you run on the Scala consoles, and they will be submitted to the Yarn and to getting the node assigned and to run them. So the last part is going to be your hands-on sessions. The reservation name is a Hadoop-June 12, so that's today's date. I have a folders in the /works, and that's my number, and then my login name. And then Hadoop/June 12. There are some example data there, small text files, and a collection of the stories. If you're interested, or if you're already bored with the lectures, you can actually read those stories. And also there is one file called exercise.txt. That's basically including all the files, all the command I mentioned, and you can practice. To start your session, just do idive-r with the reservation there. Let me quickly show the exercise text file. It's a little bit too small. Let me make it bigger. So in the exercise directories, and there's a bunch of files in there. I have the work-on.java, so that's basically the implementation I showed earlier. I also have the two bash scripts file to run word count through those Hadoop streaming using bash scripts. If you're interested, you can give that one a try. There are also a more exercise text files in there. So here I'm trying to grouping things into 5 different groups. So the first one is a basic file system command. Here's the basic things you want to run. You can try. And I also have some practice suggestion to see if you can rename a file using the file command. And what's the difference if you storing stories, which are directories in the examples, and then the text.txt. So that text file is one file, but it's a collection. It's a combination of all the text file in the stories. So I want you to really go through that to see what's the impact, what's the difference when you store one file with all the information rather than one individual, a lot of smaller files. Then the second group is about running the Hadoop application. So that's about running from exemplar jars. So I have all the command I use there, so you can starting with those. You pretty much can just having 2 terminal windows open, so you can copy paste. It should work. Sometimes there may be some small spelling things, and you should be able to search to fix that. The main things you want to play around is you can play around to see different map tasks and reduce tasks to see how it affects the running process. You can also try some other command. There's a lot of command in the example jars. I give examples where you can starting a teragen to generating a say 10 gigabytes file and then running a terasort on top of it. The terasort is another commonly used benchmark things you can do. And then if you're interested, you can do calculating pi with Hadoop. Then the third group is to show you examples on how you can compile a source code and then make a jar file, then running that jar file there with your Hadoop clusters. The word count is just a hello world program. So if you want to practice, you can actually program in something useful if you're familiar with Java. Then the first group is about Hadoop streaming. So this is exactly the same command I showed in the slide. So you can copy paste them to run them, and that will be using the bash script file. So the bash script file is not that performance-wise is not that good. So it works with a smaller data file, but it may fail for the larger files. As a practice, you could easily say, we have Python available on Wrangler. So if you're familiar with the Python, you can actually quickly write a Python version that actually could run much faster than the bash script version. We also have R installed on the Wrangler, so you could do a R scripts. Both of them is fairly simple. If you're familiar with the language, you should be able to do it. Then the last group is just run through the Mahout example I gave during the slides. So you can follow those step 1 to 5 to repeat the k-means clustering algorithms. You can also just type in the Mahout and to see other program available to see what are the things you want to run. Okay, so we will leave whatever the time we left for you to explore them and to do the practice. Feel free to really spending some time here. We will be sticking around and taking questions both in room and for the online peoples. We are trying to keep the reservation alive so you can access them over the weekend as well. So if you cannot access them now or you need to go now, feel free to play more during the weekend or at your convenience. But the reservation will be going down, I think, in Sunday. So you can see that through the ice control reservations. So any questions? Okay. So just have some fun with the examples I'm providing and just trying to go through them. Yes, sir.
What's the location of this file?
Next up, just Hadoop June 12 code example files and the data. There are some large files on the /time/data, and there's a Wikipedia down of the 2012 with the 40 gigabytes things.
Did you stop the screen?
No, I didn't. It's on. everyone's still online, and we're going to end the online session now. So the last page shows the email address to the data group and my email address. So we will keep the reservation run through the weekend. So feel free to spending some time with it. And if you have any problem to accessing it, feel free to email me. So I will try to get that resolved. Thank you very much for attending this. And maybe see you next time.